Okay, so here's our review of the graphing utility test. This one should go a little quicker. So it says use the graph of G to find the following values. So here's our graph of G. So let's look at these one at a time. So what about this first one? What's G of -1, or does it exist? Well, G of -1 is 3. It does exist, and it's 3. Right, we can see on the graph that's the value that's defined for the function. So there it is. What's the limit of g of x as x approaches -1 from the left? Well, that's as an ant is walking down the function towards -1, and he anticipates stepping on a value of 4, you can see. And then also, same thing, as an ant approaches -1 from the right, the ant was walking backwards towards -1 and anticipates stepping on a value of 4 again. Okay, so because the ant approaches the same value from both sides, the limit of g of x as x approaches -1 is 4, because the two one-sided limits agree. What's g of +1? G of +1 is 2. The limit of g of x as x approaches 1, well, as x approaches 1, the ant from the left is approaching, we'll color code this, so that's going to be green, approaches a different value than the ant approaching from the right. They anticipate stepping on different spots. And so the answer is there is no limit, because the green limit from the left doesn't agree with the red limit from the right. G, what's the limit of g of x as x approaches 3? Well, as x approaches 3, the ants anticipate stepping on the actual value of the function right there, which is a value of 4 from both sides. And what is g of 5? Well, g of 5 looks to be, there's the point right there. G of 5 appears to be 5. The y value is 5. Okay, last one. What's the limit of g of x as x approaches 5 from the left? Well, as x approaches, there's 5. So as an ant walks towards 5, it anticipates stepping on that spot right there, which has a value of 5. Okay, what about this? Use technology to approximate this limit. Well, we can do this a number of ways. We could do this. We need it to 2 places. So we could do this in Desmos, theoretically, if it's got enough accuracy, and I guess we'll see. So first of all, let's put the function in. Well, there it is. There's our function. We can see on the graph that as we approach 1, there's x equals 1 right there. So we can see that it's, the limit does exist. We're approaching a certain value. The value appears to be 2 from the graph, but we could sure find out if we plug in a value close to 1 in our function. Let's do f of 0.99999. If we go out there a ways, look, we can see that we're approaching a value of 2.00 to 2 places. We could do the same thing from the other side, f of 1.00001, right? And if we keep going out there closer, we can see that to 2 decimal places, we're also approaching a value of 2.0. Okay, so I'll take a picture of this. Oh, darn it. So there's our picture. And the answer is 2. Okay, just by using technology. We could do the same thing on our graphing calculator if we just entered this as y1 and then evaluated it at values very close to 1, right? Okay, so let's, actually I'll show that to you real quick on your calculator. So I could go up here to y equals, and I could add this function in there. So I'm going to go ahead and use my alpha F1, use my fraction template. So I've got 18 times the quantity, cube root, and where do I get my nth root? I could just do a power of 1/3, or if I go math, there's a cube root right there, number 4. We'll just use a cube root. Cube root of x, scoot to the right, minus 1, close the parentheses, divided by x cubed. So x cubed minus 1. And then we could go up to table. If we set the table, we want the independent set to ask, so we can plug in any value we want to. So then if we go second table, I could plug in a value like 0.9999999 and hit enter, and it gives us to 2 decimal places 2.00. I could plug in 1.00001, and it also gives me 2. Okay, out to that many places. Okay, either way we go, we get the same answer. All right, what about something like this? We don't really need a calculator for this. This is just properties of limit stuff. So we know if we define the limit of f of x as x approaches 6 is negative 216, then we could say the limit of f of x to the 1/3 as x approaches 6. The important thing here is that we could rewrite this as the limit of f of x as x approaches 6 to the 1/3, which is just negative 216 to the 1/3. That's a cube root, and that's just negative 6. Okay, so just the properties of limit stuff like that. Okay. What about this? So find the limit of the rational function as x approaches infinity or negative infinity. Well, we can, we did this on the non-graphing test analytically, but on the graphing test, we could take advantage of Desmos. We could just look at the graph, or your graphing calculator if you want to. So if I just, there's my function. If I just go ahead and zoom out, we can see that as we move to the right, this function is going up to infinity. As we move to the left, it's going up to infinity. And so let's get rid of that. So there's my picture. Take a picture of this for the notes. There's my picture. And so based on that picture, we know that I'm going to get infinity for both answers. Okay, this one, your graphing utility doesn't really help you much on this, but we can just go through. I put all the graphing stuff on the graphing utility test, even if it doesn't need a graphing utility. So let's just go through and cross these ones off if they don't work. So these are the things that have to be true. F of 0 is 0. Okay, that's good, that's good, that's good, that's good. F of 1 is undefined. Okay, so all these are undefined at f of 1. The limit of f of x as x approaches 2 is negative 1. Okay, as x approaches 2. So that's right there. Okay, so good. This one we can cross off. As x approaches 2, the limit is positive 1 for this guy. So that one we can cross off. And same thing here. That one gets crossed off. The limits are wrong. Maybe I shouldn't. I'll put the x down here so you can still look at the picture. The limit of f of x as x approaches negative 1 from the left is positive infinity. As I approach negative 1 from the right, I should be going up to infinity, right? And I'm not doing that. Here I am as I approach, look at this ant right here. As we approach negative 1 from the right, it's sweeping me up to infinity. So that is the correct answer. And if you want a little, I'll show you what happens when you click on these make bigger. And actually this one down here where you have a pop out, that's very useful. So that one's crossed out. This is our answer. Okay. Here's what happens. It makes it much bigger, doesn't it? Oops. I thought I had that on there somewhere. Oh, maybe I didn't. I don't know. No, I didn't. You can click on this thing and it makes it a lot bigger, and that's easier to see. Okay. What about this? Looks something like that when you click on them. So select the correct answer. The limit of f of x as x approaches negative 5 is what? Well, as x approaches negative 5 right there, it looks like from both sides we're going up to infinity. And so the answer is infinity. The limit of f of x as x approaches 6, I'm going down from the left and up from the right. And so that one, it doesn't exist. It's neither positive nor negative infinity because it has different behavior from the left and from the right. Okay, what about this one? For the functions shown below, compute the following limits or state that they don't exist. Okay, well, how could we do this on Desmos? There is a way to do piecewise functions on here. I've done it before, and I can't honestly remember how I did it. But here's a way you could do it. Okay. I wish I could remember that. If I think of it here, I'll add a little addendum to this video that shows you how. Okay, one thing we could do is we could just graph these all separately. So I've got the line, I've got 3 parts to it. I've got y equals 0. And, okay, y equals 0. Gosh, I think there's a way to do that. If I say, oh, I'm not going to mess around with it. I don't want to waste your time. So we'll graph that in blue. The next line is we could graph y equals the square root of 36 minus x squared. And then we could graph y equals 2x. So we got these 3 pieces here. Let's change that color. Let's make that one red. And let's see what we're doing. We want to know what's the limit of g of x as x approaches negative 6. Well, as I approach negative 6 is on the boundary between this behavior and this behavior, right? So what do we get for that one? As we approach negative 6, we get a value of 0 from the left, because that's this guy, right? That's the blue one. So as an ant is walking towards an x value of negative 6, from the left, he's walking right along here. And he's approaching that point right there, which looks like a y value of 0. If an ant is approaching negative 6 from the right, he's walking along the purple part, and he's approaching the same value, which is 0. We can see that on the graph. Okay, so the answer to part A is 0. What about part B? As we approach 6, from the left, we're on the purple part, right? Because look, the purple part, the square root, is what we have between -6 and 6. So he's approaching a y value of 0. As the ant approaches x equals 6 from the right, he's on the red line. And so this ant is walking backwards down the line towards 6, and he anticipates landing at 12. And so you get different answers from the right, which is on the red line, and from the left, which is on the purple semicircle. And so the answer is the limit, the second limit doesn't exist. Okay, so based on, I'll put this picture in here again, just so you have it. You could also just do this one analytically, right? You could just do this by taking one-sided limits in the piecewise function. But we were looking for, on this part, we were just looking for some technological shortcuts. So A doesn't exist for part B. Okay, what about these? Evaluate the following limits using plus or minus infinity when appropriate. So once again, with technology, these are really easy. We can use technology. Here's the function that we get, and we can just look at the graphs. So there's our function as we approach 1 from the right. Well, look, there's our asymptote, isn't it? Right? We have an asymptote at 1. So if I just let's type that in, x equals 1, so we can see that vertical asymptote. As I approach from the right, I'm going down to negative infinity. As I approach from the left, I'm going up to positive infinity. And so I can say neither thing about part C, right? Let's get a picture of this. So from the right, we said negative infinity. From the left, positive infinity. And neither for our two-sided limit. Okay. Okay, what about this? Well, we could do this same way. We could just look at a graph here. So if we look at the graph of this function, and we want to know what happens as x goes to positive or negative infinity, so we could just go ahead and change the x-axis on this one. We could just zoom out if we wanted to, but if we want to keep the y-axis the same, and that's fine to do, we could probably see the answer right there, can't we? It's 5 on both sides. If you have one that's a little harder to read, remember, you can always go up to the wrench, and I could leave the y-axis with the same limits, and I could even make it a little bit smaller. Like I could go from -1 up to whatever, 9 point something. And on the x, I could do something like go from -100 to +100. And then you can see pretty easily there that that's eventually sticking to the line y equals 5. Isn't it? Right. If let's put this one on top. So now the red one's on top of the asymptote. Okay. So you can see either way, the answer's 5. Get a picture. I get 5, both to the left and the right on that one. Oh, what did I do there? Somehow I pasted. What did I do? I think I pasted the wrong. I don't know what I did. Something weird. Oh my gosh, what did I do? There, I got it fixed. So there's my picture. You can see we're approaching 5. Okay, moving on. What about this? Okay, so on this one, they want to know what are the equations of the vertical asymptotes, if there are any, horizontal, if there are any, and oblique asymptotes, if there are any. Well, we could graph this one again. So there's my function, right? And we can see there that the vertical asymptote is at -3, right? And we can just plug that in. There's our vertical asymptote. Now, what about the horizontal asymptote? You can't really do this one graphically, right? But what you could do is you could say, I mean, we can just divide this thing out using synthetic division. So let's do that first, just to remind ourselves how that works, right? We got the vertical asymptote part. And if we use synthetic division on this, we've got the coefficients 1, 0, -6. There's our remainder box. Our 0 of the denominator is -3, so we get 1, -3, 9, and 3. Not that we care what that is, right? That tells us that this is equal to x minus 3 plus a remainder of 3 over x plus 3. And if I take the limit of f of x as x approaches infinity, we can see that that term's going to go to 0. And so here are the terms in our polynomial answer. So that's our slant asymptote, right? What can you do? How can you utilize the graphing calculator on this one then? So there isn't a horizontal asymptote. We can see that. So how could you kind of use this graphing utility to your advantage? Well, one thing you could do is you could check yourself on this one, right? We could plug in our equation for the asymptote, which was x minus 3. There it is, right? So it fits. And you could even, if you, well, you can see that the ratio of the leading terms is just x, right? So you could even do something like this. You could even say something like y equals x plus, call it, what am I going to call it, like a or something, right? And we'll add a slider for a. And then we could pick values of a. Just, we know that the first term is going to be x because the ratio of x squared over x is x. And then we could just try different values until we get one that's going to work. And why don't we set this up so we can make the steps go in ones. So if I go -10 to 10 by ones, then it's a little bit easier for me to drag this value along. So that looks pretty good right there, doesn't it? Right? If we center that thing, we can see that that's pretty symmetrical. So we could get it that way too. We could just kind of graphically see that a is -3, which lines up with what we got, doesn't it? Okay. So either way, add this to the notes. Oh, darn it. There we go. Okay. What about this? Same thing, right? We could really do the same thing. We could divide this one out using long division. We did an example like that in the last review, so I'm not going to do it. We already did one of those. We could, if I grab the graph, where is that graph? Maybe I didn't make that one, so we'll use this last one, and we'll change it a little bit. So the top's going to be negative x cubed plus x squared plus 5x minus 3 over x squared plus 4x minus 5. Okay, and so this time, if we do the ratio of our leading coefficients, we know that negative x cubed over x squared is negative x, right? Oh, we can get rid of that. Is negative x. So this time we're going to get the result that's going to look like negative x plus a. We got to figure out what a is. Well, we could just drag this value of a until we end up getting something that's symmetrical. And that looks pretty good right there, doesn't it? Right? If we zoom out a little bit, we can see that that's, if I center this thing, it's approaching the asymptotes at approximately the same rate on both sides. And so we could at least check ourselves that way. If we did the long division, we can see here that 5 appears to be the answer. So, or like I say, just do the long division. That'll work too. If you want to go through a long division problem with me, why don't we do that during office hours? Come on in and I'll go over it with you during office hours. Okay, so that's what we got. And we can see, sure enough, we get x, negative x plus 5 is the correct answer. Oops. And then you just have to pick the right one down here, right? The one that fits the asymptotes. Now on this one, we don't have to do any fancy one-sided limits because we've got the graph. It's right there, right? So we can just look at the one that has the right behavior. So what's the behavior going to be on this thing then? If we put in the vertical asymptotes, the vertical asymptotes appear to be, if I zoom in a little bit, they appear to be at 1. X equals 1. Make that a different color. Let's make that green. And what's the other one? The other one appears to be kind of halfway in between. So this is, once again, this is kind of, when you see something like this here, it's hard to zoom in properly. So let's do this one manually. Let's have the x values stay the same, or we could even separate, we could even space those out a little bit. So let's have the x-axis go from like negative 20 up to positive 5 or something. And let's have the y-axis get really big. So the y-axis, we could go negative 100 to positive 100. And now we can see that axis. We can see that 5 is the right answer, isn't it? Or negative 5. There are vertical asymptotes. And if we put this thing, let's put this below them so it's on top. How do I do that? There we go, like that. now we can kind of see what's going on here, right? We can see which graph. I'm going upwards on this asymptote from the left. I'm going downwards on this asymptote from the right. I'm going downwards on this asymptote from the left. And I'm going upwards on this asymptote from the right. And then, of course, on the tails, they're just going to stick to this oblique asymptote. So we have to figure out which one matches that. I'll take another picture. Well, which one matches it? You can see that this is the correct one when I blow them up, right? So that's pretty straightforward. I mean, that's almost like legal cheating there because you have access to a graphing utility. Okay, let's see, last couple. What about something like this? Analyze the graph of the function. Okay, well, we can just graph it. So there's our function. And what are they asking us about this? They want to know what's the domain. Well, we can see that there are some vertical asymptotes here at, looks like -11. There's one vertical asymptote, and x equals +10. There they are. So that part we can see right away. +10, -11, and it's multiple choice. So, I mean, you can just check these easily on the graph. What are the equations of the vertical asymptotes? Well, they just go with limited restrictions on the domain, right? We get x equals 10, x equals -11. We've already got those graphed here. And then the last part, they want to know any horizontal or oblique asymptotes. Well, we could just zoom out effectively, couldn't we? If we zoom out, we can see that we're going to have a horizontal asymptote that's greater than 0. Let me take 2 pictures for the notes. Here's one. So this is the one we can use for parts A and B. So there's the one for parts A and B. Now what about part C? For part C, how do we know it's y equals 1? Well, I could use the same graph. Let's go in here and tweak the axes, tweak the window a little bit. Not the axes, the window. Let's leave the y the same, but let's make the x's go from -100 to +100. And then we can see that it's got a horizontal asymptote at y equals 1. So I can turn these off. There's my horizontal asymptote. Okay. And then finally these delta epsilon ones. So what about this? They say let f of x equal x squared plus 3 And note that the limit of f of x as x approaches 0 is 3. Okay, we can see that on Desmos if we graph this function. So there's the function, right? F of x equals x squared plus 3. We can see if I put this in, if I open up an ordered pair and just put something comma something, it graphs it as a point. So I'm doing in parentheses 0 comma f of 0. And then it's calculating f of 0 from this function, which we can see is 3. And look, we get the point 0, 3. So that's the point the ant is approaching, right? We can see that's the limit. Okay, the question is, find the value of delta, the maximum value of delta, such that epsilon is 2, right? The distance between f of x and the target of 3 is 2. Okay, we can do this graphically. We could either be fancy with this and we could do something like say, okay, g of x equals f of 0, which is just 3. I could just plug a 3 in there, plus d, and I could use the slider. And we want d to be how big? Well, if epsilon is 2, we're going to let d equal 2 in this case, right? Because we want to know, we want to go up 2 and down 2, but because the function never goes down, we only need the top limit, right? We want to be within 2 of our target value of 3, so we need to be inside of the x values that give us that adequate accuracy, right? Well, where does that happen? I can go up here and click on the intersections, and I see that my function has a y value of 5, which is 2 bigger than 3, when x is positive or negative 1.414. So the width of that interval from x equals 0 is 1.414. So it's just a rounded square root of 2, which would make sense, wouldn't it? Okay, so that's one way to do it. The other way we could do it is we wouldn't have to be so fancy. We could just go down here and say, okay, we've got the line y equals 3. There's my line. If I add 2 to that, y equals 3 plus my epsilon, which is 2, well, there's the intersections we're looking for. Either way, okay, gives us our answer. So for the first part, our answer is 1.414, right? Let's get a picture of that. So there's for the first part. For the second part, if we do the same thing, for the second part, what's our delta or our epsilon? 1.5. So all we got to do is go back and we've just got to change this to 1.5. Changes our answers a little bit. That's what we get. We can see that the width of the interval from 0 is now 1.225 to the left or the right, and so that's my delta. Okay, and then finally, this one, we don't even need the graphing utility. They give us the graph. If epsilon is 3, we would just look on our graph here. How far can we move horizontally from our limit? As x approaches 2, the limit is 6 of our function. We don't know what the function is, but we don't care. How far can we move horizontally and stay within 3 of our target value of y equals 6? So we can just look on here and draw some horizontal lines to help ourselves out. So 6 plus 3 would be 9. And so we want that intersection right there. 2, 3, or that intersection right there. Either way, look, our delta to the left or the right is 2. So the answer is 2. What if we made epsilon 1? Well, if I made epsilon 1, if I'm going up 1 or down 1, six plus 1 is 7. 6 minus 1 is 5. So there's epsilon. And we can see the intersections are there and there. And that appears to be a delta. Delta equals 0.5. Okay. All right. So hopefully that's helpful. I'm going to call her quits. I'll see you guys later.